For today's algorithm, we're going to be discussing relational algebra. In this video, you're going to get a quick introduction to relational algebra and some of the basic operators, some of the core operators that you're going to need in order to use this algebra. But first, let's talk about what is relational algebra. Well, relational algebra is an algebra with semantics used for modeling the data storage in relational databases or defining queries on it. So the main application of relational algebra is providing a theoretical foundation for relational databases, particularly query languages for such databases. One query language that might come to mind is SQL or SQL. So as the name suggests, relational algebra discusses algebra on relations. Now, what is a relation? Well, a relation is a set of tuples, which we'll define in a moment, defined by a set of attributes, which we'll also define in a moment. So in relational algebra, or in SQL, you might consider these to be tables. Now, as I said, these relations are defined by attributes and contain tuples. So what are attributes? Well, attributes are the named type definitions that define a table. In SQL, you might consider these columns. Each attribute represents what type should exist in that column and what the aliases for the values inside of that column. And lastly, tuples. Each relation is made up of tuples. Now, tuples are the contents of a relation, and each cell corresponds to its related table attribute. In SQL, of course, you would consider these to be rows of a table. So the only thing left that you need to know about this is that relations in relational algebra are sets. And any query operation on a set of relations produces a relation as a result. So all of these operators produce relations as their output. In SQL, you do not have this restriction that your relations are purely sets. So this is a distinction to keep in mind if you're coming from SQL. So let's take a look at our first operator. Our first operator is the select operator. Now, the select operator takes two parameters, a relation and a predicate. Now, the relation can either be a table or another subquery. The reason we know it can be a subquery is because every query outputs a relation, so therefore it's valid in terms of the input parameters. Now, predicates can be simple or complex. They can be simple, such as equals, not equals, less than, greater than, all of which these simple predicates take two expressions as parameters. So it'll be an expression A is equal to an expression B, or an expression A does not equal to an expression B, and so on. On the other hand, you can have complex predicates, which will take two subpredicates or more and combine them using complex operators such as and, or, not, right, or whatever else. So those are the inputs to a select operator. Now, combined with the select operator, that's very common to use is the project operator. Now, the project operator, symbolized by the pi symbol that we all know from mathematics, takes a relation as a parameter, as well as a set of attributes. Okay, so it's two parameters, one being a relation and one being a set. Now, pretty much the relation, of course, can either be a table or a subquery, once again, because again, subqueries result in relations. Now, what this project is going to do is it's going to give you the table resulting in only the columns or only the attributes that are contained in the set that you passed into the second parameter. But we're going to take a look at an example of what this might look like. So from our last video on indexes, you might recognize this table we're about to show. This is the Sharp CS table. By the way, if you want to learn about indexes, you can click the title card in the top right-hand corner to go view that video. So here is our example table, Sharp CS. Now, the Sharp CS table has three attributes. The first attribute is an ID. The ID is an integer. Our second attribute is a title, which is a string. And our third attribute is the topic attribute, which again is a string. And it has, as you can see, 8 tuples at the moment. Now, we're going to do an example relational algebra query on this table and look what the result is. Now, the query we're going to want to run right here is going to be a project on just the ID and title columns. So our set that we pass into this project operator is going to be the tuple ID title, those two attributes. And it's going to take as its relation a new expression, which is going to be a select with the parameters topic equals B plus trees, or because it's going to be a complex predicate, topic equals number systems of our table here, sharp CS. So of course, because this select returns a relation, we can pass this into the first parameter of our projection. So there's our query. Now let's look at what the result is going to be. So to look at this query result, we're going to work from the innermost query outwards, just to make it as intuitive as possible. So the first thing you'll notice here is that we have this table with all sorts of different topics, but we're taking a select on two predicates, one being that the topic is either B plus trees or the topic is number systems. So if we look inside of our table, we see that there's two rows, right, that have number systems and B plus trees as their topic. So immediately we're going to cut out those two rows from our table and operate on those for our projection. Now the projection only wants to select the ID and the title column. So once we pulled out these rows, which will give us their IDs, their titles, which are binary number conversion and types of indexes. By the way, great video. You should definitely go check that one out. And the topics. Once we pass this new sub-relation into our project as its first parameter, we're only going to want the ID and the title column. So what we're going to do is strike the topic column or the topic attribute column, and we're left with the relation that contains two tuples, both of which are related to number systems or B plus trees. Now, what is the intuition behind this in terms of why would this be something you'd ever want to do? Well, consider you are traversing YouTube and you want to learn about B plus trees or number systems. So you're going to put that into your query, right? You're going to make that your query. Now, YouTube needs to somehow give you back information that will tell you these are the videos that you want to watch. Now, it could just give you all the videos in the entire site, which would be giving you basically this whole table. That wouldn't be very helpful for you. So the first thing it's going to do is cut down the table to just the topics that you selected, right? So the first thing is, oh, you chose the topics that you want to watch. So then you'll get this table that has, an ID, the title, and the topic. But you already selected the topic. So is the topic column really necessary? Like, does YouTube really need to provide you with the topic as well? Well, of course not. So we can strike that column, and Google might choose to, or YouTube might choose to only give you the information that you need in order to watch the video. So maybe the ID is the link to the video and the title so that you know, oh, I want to watch types of indexes because that title sounds interesting to me. So that's the first two operators. Let's look at the next operator. Now, the next two operators, actually. Both of these two operators are set operations. So if you know how to work with sets, these should be pretty intuitive. The first one is the union. Now, the union takes two parameters, both of which are relations, and returns a relation that contains all the tuples in both of those two input relations. Now, the only way you can use a union in relational algebra is if both of the two tables contain columns or contain the same attributes, right? This is not a restriction that you'll find in SQL, but it is something you have to consider in relational algebra. So let's quickly take a look. Yeah, and by the way, what that means in reality is that they're union compatible. Those two tables are union compatible if they have the same attributes. So let's take a look at two example tables. Let's make one table, we'll call it T1, that has two attributes, C1 and C2, each of which contain the following tuples, A1, B2, C5. Now let's make a second table relation, T2, with the same attributes, C1 and C2. This one's going to contain the tuples X, 9, Y, 13. These tables will show up later as well, but let's operate on these for right now. So T1 union T2 is going to result in the table that contains all of the rows or all of the tuples of both of these two tables. So of course, we're going to start with A1 and then get B2 and C5 and X9 and of course Y13. I noticed that we ordered these such that T1 is above T2, but realistically these are sets, so it's not super important. However, in SQL, of course, the order would matter because they're not sets. So let's take a look at set difference. Again, if you work with sets before, this should be pretty intuitive to you. Basically, the set difference operator takes two parameters, both of which are relations. And once again, they have to be union compatible. It's going to result in the relation that it contains all of the tuples in R1, the first relation you passed in, subtracted from all the tuples in R2. So any tuples in R2 should not appear in this final relation. This is the way you want to think about this. So let's take our example from above, of course. Our example from above being T1. And let's maybe construct a second table in order, because T1 and T2 set difference wouldn't result in anything special. It would just result in either T1 or T2, depending on which side you put them of the set difference operator. So we're going to have to construct a new table here that actually would change with set difference. So let's make this one T3, and it's going to have the same attributes in order to be union compatible. And let's say that in T3 we have the columns or the tuples A1, B2, X9. So you can see here that A1, B2, X9, A1 and B2 both appear in T1, which is good. So what we want in order to demonstrate set difference. So when we take this set difference of T1 minus T3, we end up with a very small relation with the same two attributes. Of course, we're union compatible, so we end up with the same attributes. And only two tuples left in this relation are C5 and X9. So that should be pretty intuitive. This leads us into our next operator. Our next operator is the Cartesian product, denoted by an X, similar to multiplication, because it actually functions exactly like multiplication. So the Cartesian product is going to take two relations as parameters, just like the union and just like the set difference. Again, if you're familiar with sets, this should be intuitive to you. And it's going to return a result that is a larger relation in terms of attributes, because it's going to have as many attributes as there are in R1 plus as many attributes as there are in R2, and going to pair every tuple of R1 with every tuple of R2. So if we have 3 tuples in R1 and 3 tuples in R2, our final relation should have 9 and so on. That's why we call it Cartesian product. This is exactly how product works in real life. Another term for this is a cross product or a cross join. If you're working in SQL, you can call this a cross join, and that's actually an operator as well. But let's take a look at an example of this. So we'll use T1 from above. Once again, since we already have it, we're familiar with it. It contains A1, B2, and C5. Of course, its attributes are C1 and C2 because we need to be union compatible. So we're going to keep the same attributes. And T2 is going to be the same as above as well. It's going to contain the attributes C1, C2, X9, Y13. So these are our two relations, and let's take the cross join of these. Now the cross join is going to be a little bit large, but we'll manage. So of course, at this point, what you'll notice is that although the names of T1 and T2, the attribute names, are the same, you really have to rename one of them here. We haven't talked about the rename operator yet, so we're just going to call them T1.C1, T1.C2, T2.C1, and T2.C2. This is, of course, something this is also totally a viable way to do this. So once we have our new schema set up, so this is the new look of our table here, we now just have to fill it in, and we're going to fill it in exactly as I said. We're just going to take every single column of T1 and pair it with every single column, every single tuple of T1 and pair it with every single tuple of T2. We're not going to do all of them here because it's pretty long, but you get the idea, presumably. So that concludes the cross join or the cross product. Lastly, and I was just speaking about this, we need the rename operator. The rename operator, of course, will make this cross product cleaner and more professional and more realistic, right? So the rename operator is pretty simple. We don't really need an example for it. All it's going to do is it's going to take the parameters, a relation, a string, which we'll call str, and a set of strings, which we'll call str set. So what do each of these mean? Well, the relation, of course, is the thing we're going to be operating on. The str, or our first string parameter, is just going to be the new name for the relation. So let's say the relation was named relation, as you see over here. It will now be named str if these were literal meanings. Lastly, the set of strings, which we call str set, is going to be the new names of the attributes of this table. Like I said in the above example, we probably would have wanted to rename the attributes of T2 in order for the cross product to be more meaningful. So that wraps up all the core operations that you need in relational algebra. Let's, at this point, take a look at a final example that combines a lot of these operators together. So for this final example, we're going to be working on the same tables as above, T1, which contains A1, B2, C5. We've seen it a million times already. Of course, the attributes are going to remain C1, C2, on purpose, of course, so that we can operate on these and rename them. C1, C2 of the next table, which is table 3 as well, are going to remain named the same, and the members of T3, which are A1, B2, and X9, are going to remain the same as well. All right, now let's write a big query on this that uses everything we just learned. So we'll start by projecting, right? We always want to project, choose the column we want. In this case, let's say we only want C2. We just want the numbers for whatever reason. So we'll do project C2 on. Now let's cut this down a bit. Let's say we only want tuples where the C1 attribute is greater than C. And what we mean by greater than C in this situation is that the C1 ASCII value is greater than the ASCII value of C. So anything higher than C in the alphabet, such as D, E, F, totally valid. Anything lower than C, including C, C, A, B, not going to be selected here. And we're going to do, we're going to take the select on T1, but of course selects can take subqueries as inputs. So we'll do T1 cross product. Now, as I said before, we needed to rename, but we didn't. So now we're going to rename. We'll call this new table temp. So we'll say P temp is the first parameter. B1, B2 is our second parameter because we're going to rename the columns here. And we'll call the table, and on the table T3. Of course, we don't really need to rename the table to temp, but just to show that this operator, or how this operator works, we're going to do that anyway. And that's our entire query. So once we have this query written, let's actually take a look at what the result of this is. And we'll break it down into parts just so it's easier for you to comprehend as you're trying to parse through this relational algebra. So the first result that we need to compute is the rename. Now the rename is pretty easy. We can just strike the name here of T3 and we can replace it with temp. And we can strike C1 and C2 and replace them with B1, B2. And there you go. So we've already computed the rename operation. The next one is a little more cumbersome. It's the join. So now we need to take every tuple of T1 and combine it with every tuple of temp. Well, okay, so this is a little less nice because now we have 4 attributes here. We need C1, C2, B1, my bad, and B2. So those are our 4 attributes, and we fill them in like so, with each tuple of T1 pairing with each tuple of temp. A1 with X9, B2 with A1, and so on. In reality, right, we'd like to select first before we join, but because we wrote the query this way, we're joining first and then selecting. Not a problem. And lastly, C5, X9. So there's our first sub result here. Finally got all of those values in. And now let's actually do this select operation. So we're going to select where C1 is greater than C in terms of ASCII, of course. Now, our situations where C1 is greater than C are actually smaller than you'd think because we only have 3 cases in which this is the case, and that's the bottom 3 rows here. So we're going to cut everything out of this table except the bottom 3 tuples. Now, lastly, we want to project only C2, which means we're going to cut the entirety of C1 and the entirety of B1 and B2, leaving us with just this kind of funny looking relation that has C2 as an attribute and 5, 5, 5 as its values. Well, that wraps up our tutorial on relational algebra. If you found this tutorial helpful, don't forget to like, comment, subscribe, hit the little bell icon so that you know when we post our videos. Share with all your friends, family, loved ones, neighbors, people you don't even know and you just met. Just share it, and that'd be a very big help to us because we're trying to get off the ground here. Otherwise, if you want to learn more about these database kind of stuff, we're going to have a whole series on it, so stay tuned for that. And as always, we'll see you in the next video. Later.